Welcome to this session. This session is going to deal with solving equilibrium problems of the general nature, meaning not solubility, not acid-base. Could run into some gas law types, could run into some concentration types, could run into those that cross over between the two. But in any event, this is where we're headed, and I am really glad you're here. My name is Renee McCormick with the National Math and Science Initiative, and let's get started. So, reaching way, way back, I know, you weren't even born yet, it's 1983, but sometimes those problems back then are actually really good because they're kind of pure, and they don't, like, birdwalk off into much thermo or kinetics or electrochem or anything that you may or may not have had yet, all depending on what sequence your teacher's following. So this particular problem was a 9-point problem, and you're doing well if you can get 5 points of that. So what you should do at this point, if you have not already, and you've heard this speech 100 times, is you need to pause right now, and you need to get that AP worksheet off of the wiki page or from your teacher, and you need to work this problem before me. If you've tried that, then let's get at it. If you have not, then shame for shame. Put me on pause, work it, and then come back to me in a bit. All right, let's read and see what we can figure out. Sulfuryl chloride, SO2Cl2, is a highly reactive gaseous compound, and when heated, it decomposes as follows. The decomposition is endothermic. So right now, you should just go ahead and say that means it requires heat as a reactant, and throw that in there in case Le Chatelier's principle comes up somewhere. So that if I added heat to the system, I'm going to add, it's like adding a reactant, it's going to shove the reaction to the right. If I take away heat, it's like removing a reactant, and it's going to shove the equilibrium back to the left. Don't try to make that hard. There's lots of multiple choice points associated with that concept. A sample of 3.509 grams of it is placed in an evacuated 1 liter bulb, and the temperature is raised to 375 Kelvin. How kind that they gave me Kelvin. They also gave me a volume, and it's all gases up here. And I'm envisioning maybe some Pivnert coming on. Also, I'm thinking that if I need change the number of moles for the politically correct equation, that's going to be a +1, because I see 1 mole of gas on the left and 2 moles of gas on the right. So it increased by 1 mole of gas, hence the +1. And I have grams, which means I can get to moles if you make me. So, indeed, what's the first thing they ask me? What's P? Well, given a V, a T, the ability to get to N, you already know R. I'm thinking Pivnert. I'm thinking ideal gas equation. So, let's do it. PV equals nRT, and you want to know the pressure in atmospheres of the bulb if no dissociation had occurred. So, haven't made any of these products yet, only reactant in the bulb. So, therefore, pressure going to be nRT over V, and that's going to be 3.509 divided by. I use 2 decimal places generally off of the periodic table, so you should have your handy-dandy periodic table, and you should figure out this molar mass. 32.06 for the sulfur, 32 for 2 oxygens, and 70.9 for the 2 chlorines, and all of that is grams per mole. So that is my N term, and then 0.0821 liter atmosphere mole Kelvin for my R, and then my T they gave me 375 Kelvin. All of that divided by SAD 1.00 liter. So my liters cancel, my grams cancel, my 1 over a mole cancels my mole, and my kelvins cancel. I'm left with atmospheres, so that's a good thing if I want pressure. I never even bother working the calculator until I've checked the units, because what would be the point? Oh, that's not an 09, that's not a G, that's a 9. There's a G right there that gets canceled. Okay, so now let's try it. 3.509 divided by all of that mess, 32.06 plus 32 plus 70.9. There's a chance I'm going to need that moles later, so I'm going to go ahead and write it down now, just in case I need it. It came out nice and even with all those zeros at the end of 0.026. Okay, so that number, I can just carry on, right? times R. Okay, times, please store R in your calculator as R. Times 375. All divided by 1, so I don't even need to bother with that. So there we go. So we come out with a pressure of SO2Cl2 equal to 0.800 atmospheres. That's 3 sig figs. Is that a good choice? 4, 3, 3. Yep, I'm going with 3. All right, let's talk about storing that R if you haven't done that. You need to just put R into your calculator, 0.0821. And you need to use the store button right here. And a little arrow will pop up on your screen. And then you can go alpha, and the R lives above the multiplication sign. Just be sure to hit enter to make it stick. And then anytime I want R, I'm not going to risk mistyping 0.0821. Plus, I'm in a hurry. So I'm just going to go alpha and the multiplication sign to get my R back on my screen. So it stores it as the variable R. You should have quite a few things stored in there by the time you take the AP exam. When the system has come to equilibrium at 375 K, the total pressure in the bulb is found to be 1.43 atmospheres. Calculate the partial pressures then of SO2, Cl2, and SOCl2 at equilibrium at 375. Enter rice table, stage left. All right, make myself a little more room. What was this reaction again? There we go. Initially, I had 0.800 atmospheres. Let the problem lead you. They just had you figure out the initial pressure before the reaction started, meaning none and none of these exist. So you get to use it in Part B. Let the problem lead you. I used to write for the AP Chemistry exam. I'm telling you, they've been trained to design problems in a student-friendly way that follow a logical thought process. I know at times you think it's illogical, but I promise it's not. It's really logical. Let the problem lead you. Resistance is futile. So since this is a 1-to-1-to-1 stoichiometry across the board, say a little prayer of thanks for that. I'm going to lose some of this as it reacts, and for each one I lose, I make one each of those. So there is my change. So my E line in terms of X is 0.800 atmospheres minus X. Just adding these two lines together. Adding these two lines together. And I get X, and I add the next two, and I get X. All right, so what do I know? They told me that the pressure total, I like to work off to the side sometimes, pressure total is going to equal 1.43 atmospheres, which equals the 0.8 minus X. I'm going to drop the zeros for now. Minus X plus X plus X. So what do we get? If we simplify that, we get 1.43 atmospheres equals, that cancels that, 0.8 plus X, solve for X. X equals 1.43 minus 0.8. So 1.43 minus a nice round 0.8. And I get 0.63 atmospheres. Okay, so tell me what I just did. I knew a total pressure. I used Dalton's law of pressure, which is the easiest gas law in the whole wide world. Total pressure equals the sum of the parts. So in this container, at equilibrium, that's what this is saying, at equilibrium, I have 0.800 minus X, plus X, and plus X. So I just simply used that and set the total of 1.43 equal to 0.08 minus X plus X plus X. Simplify. Solve for X. X is 0.63. So the E line is that this is 0.63, and this is 0.63. How many sig figs should I have on here? I'm going with 3. Is it 0.63? Oh, yeah, it's going to come out even. And this is 0.8 minus 0.63, which is 0.17. And there we have it. There's nothing else I can do. You might want to double check, make sure it all adds up, but it does. 0.63 and 0.63 is 1.26 plus 0.17. It's going to get me right back to my 1.43, so I'm good with that. So there we have it. So what they want? Calculate the partial pressures of all of these at equilibrium. So there are your answers. All right, then part C, give the expression for the equilibrium constant, either Kp or Kc, for the decomposition of SOCl2 at 375 Kelvin. Calculate the value of the equilibrium constant you've given and specify the units. So I get to choose Kp or Kc. Well, dang, you just led me to atmospheres. I'm going with Kp. So Kp is equal to the pressure, I'm looking back at my balanced equation, of SO2 products, pressure of Cl2 divided by the pressure of SO2Cl2. So I'm going to plug and chug. 0.63 times 0.63 over 0.17. So 0.63 quantity squared divided by 0.17. Yes, it can really be this easy. And you come out with 2.3 for Kp. Now, if you had done Kc, I'm not sure what you come out with, honestly. I don't think I did that. So 0.23, I can figure it out real quick. Let's see what it would come out. Just for fun. This is just for fun. Kp equals Kc RT to the delta N. So therefore, and this is going to be a neighborhood, okay? Kc would then equal Kp divided by RT, and I know that my delta N was +1. I figured that out earlier. So that would be 2.3 divided by 0.0821. That's a point, not a 1. What was T again? 375. And that quantity is just raised to the 1. So, okay, so my 2.3 that's sitting in my calculator divided by parentheses alpha R times 375. So if you did Kc, it's approximately equal to 0.76. 0.076. I didn't say that right. 0.076. All right, so not necessary. That's just me in case you went to Kc. I don't know why you would, because that was a harder calculation. Because you'd have to go back and figure out the concentrations, but you could do it. If the temperature were raised to 500 Kelvin, what effect would this have on the equilibrium constant? Well, we were working at 375. We already said it was an endothermic reaction. I'm trying to get you to quit being a defenseless student and take the pieces that they give you and work on the stem of the problem before they ever start asking you a bunch of questions so that you don't get scared. So they told me it was endothermic, which led me to put that heat right there, which means if I'm going to raise the temperature, I'm adding heat into the system. Adding heat is warming it up. It's just like adding a reactant. Therefore, it's going to shift this direction. And when it shifts that direction, what's going to happen on the equilibrium constant? Well, what is the equilibrium constant? It's a proportion of products over reactants. So what's really going to happen, if I shift to the right, then the products are going to get much larger and the reactants are going to be smaller in quantity, okay, in magnitude. So that means that I'm really going to get a greater value of K. All right, so you just got to put that in words. K increases. The value of K increases. You don't quit there. Since increasing the temperature of this endothermic reaction shifts the equilibrium to favor the products. Therefore, K is proportional to products over reactants. Therefore, K increases. Okay, a kid who's going to make a 1, 2, or 3 on this exam may stop at the value of K increases. You may or may not get credit for that. Matter of fact, I don't think you will, because it's a coin toss. Flip a coin. They're not going to give you any credit for that. You're going to have to explain why. That's why it says explain briefly. So the value of K increases since increasing the temperature of this endothermic reaction is like adding reactants to it. So it's going to shift the equilibrium to the right. It's going to shift it to favor the products. It's going to shift it away from the reactants. Loads of different ways to wordsmith this. But the big idea is that you communicate, you know there's a shift, you know it's to the right, or to favor the products, and that you know that K mathematically is proportional to the amount of products over reactants, and the numerator is going to increase while the denominator is decreasing, and the numerical value of K then increases. So you have to get that explained in its entirety to earn that. Oh, I should probably do the breakdown on points before I leave it, huh? Because I know that's what you care about. All right, so let's come back and work through that for a second. 2 points for part A, 1 point for this, and 1 point for being able to calculate the number of moles. It ended up I didn't need that number again, but it sure was nice to have it in case I did. Part B, 3 points total. 1 point for this, 1 point for this pair, and 1 point for being able to do this substitution even if you goofed up the math. So that 1 point for knowing what to do, 1 point for doing it correctly. Part C is a 3-pointer. You get 1 point here. Oh, actually, you get all 3 points. No, you don't. You get a point here for the substitution. Even if these numbers were wrong up here on your E line up here, if you subbed them in properly and worked the numbers correctly, the reader would get the calculator and make sure that worked for you. Make sure you did it right. So 1 point for the expression as well. So 1 point for the expression. That's why I make you write it. I know you don't want to, but I'm telling you it's worth a point. And then plug in properly from your numbers above, and then actually use your calculator properly. So that was pretty generous, 3 points. And if you went through the KC thing and you got to 0.0676 and you showed all your work, you still get 3 points. And then finally, part D was only worth 1 point, but it was easy. So 1 point with explanation. Try to agree with yourself. Reread your explanations before you turn your paper in. All right, moving on through the 80s. Let's go to 1988. Clear the calculator for the new problem and see what we have in store for us here. At elevated temperatures, SbCl5 decomposes. Okay, they just told you. Unless they give me something numerical to dispute this. They're saying at elevated temperatures, heat's required for this to decompose into SbCl3 and Cl2. See all those gases? 1 mole of gas on the left, 2 mole of gases on the right. Delta N equals a +1. As shown by the following equation. Stop here. What do you think they're going to ask you to do? Let's see if we can put together about 5 points worth. Write a K expression. That's probably going to be worth a point. Probably do a Kp, Kc conversion. Not necessarily, but probably. I'm glancing at part A. I'm seeing grams, molar mass, liters, temperature. I'm expecting to have to do a PIV-NERD at some point, which is going to be worth a point. Just getting the moles from that molar mass and such may be worth another point. I'm up to 4 so far. Then we're doing, I see pressure in part 2. I'm looking at percent decomposition down there. When equilibrium is established, I may have to do a Rice table for some more points to actually end up getting 10 points out of this problem, or 9, however many it was worth. I think this one was worth 9. But I do have the fact that the mean was equal to 4.95. So you better get 5 points on this. So I think it was either 9 or 10 points. I'm not sure which. All right, so I'm trying to get you to think, instead of react. Think. So, an 89.7 gram sample of this SbCl5, antimony pentachloride gas, molecular weight, very kind of them to give me that, 299.0 grams per mole, is placed in an evacuated 15-liter container. You just gave me V. At 182 Celsius, I'm not going to be tricked by that. 182 plus 273 is 455 K. That's a T. What is the concentration in moles per liter in the container before any decomposition occurs? Calculate moles. They gave you liters. Easy enough. So molarity equals moles per liter equals the grammage, 89.7 grams, divided by the molar mass of 290, oops, so I'm writing 229, 299 grams per mole. That's all my numerator. Over 15.0 liters. So 89.7 divided by 299. That's my moles, that's my numerator, divided by 15. 0.02. How many sig figs? 1, 2, 3, 1, 2, 3, 1, 2, 3, 4, 1, 2, 3. I'm going with 3. So I got to put 2 more zeros out there to make that 3 sig figs. The zeros in front of the 2 don't matter. For a 0 to be significant, it must be both terminating and right. The first 0 is to the right of the decimal. The last 2 zeros are terminating and to the right, plus the 2 significant. Now I got it. 3 sig figs. I bet a lot of you missed that point, because we take a point away if you do the sig figs wrong. So 1 point here, and 1 point for getting the moles. And this moles was 0.3. Now, so how pretty it was. So if you wrote it that way and did that part in your calculator, or if you did it the way I did it and showed how you got it, either way, you get a point for that. So what is the pressure in atmospheres of the antimony pentachloride in the container before any decomposition occurs? These are what I call pity points on an equilibrium problem. You are getting some serious stoichiometry points here because you don't know squat about equilibrium. You still can solve something. So they're giving you both a stoichiometry molarity moment and a pressure moment. Therefore. So what is the pressure? It's going to be equal to nRT over V, which is going to be equal to my moles, 0.300 moles, times 0.0821 liter atmosphere mole Kelvin, times 455. Can't tell you how many kids will put that in as 182. Over volume of 15. Okay, let the cancellation fest begin. Cancels, cancels, cancels. Left standing atmospheres, that's an excellent unit for a pressure. So therefore pressure equals 0.3 times alpha R times 455 divided by 15. If I punched everything in right, I come out with 0. How many sig figs? I'm sticking with 3. 747 atmospheres. And that also is worth a point. Getting this temperature conversion, worth a point. It's kind of cheesy. So how many points have you gotten so far if you could do stoic? 4. So 4 of the points on this problem, half of them pretty much, are coming from things that are not equilibrium. On question 1, mind you. Clear that out. Part B. Because all that other was part A, huh? If the antimony pentachloride, I'm going to need more room, is 29.2% decomposed when equilibrium is established. They just told me X. And that X was equal to the original whatever of SbCl5, whether it's pressure or whether it's concentration, minus 0.292 times original. And that's still 455K. Calculate the value for either equilibrium constant, Kp or Kc, for this decomposition reaction and indicate whether you are calculating Kp or Kc. Choices. Well, I'm going to do Kc. So R equals SbCl5 in equilibrium with SbCl3, and Cl2. So why did I choose to do that? Because way back up here, they had me calculate 0.02 molar. So initially, 0.0200 molar. None, none. Because they said before the decomposition reaction begins. Now, the change was, since this is a 1-to-1-to-1 stoichiometry, cheesy, makes it easy, minus x plus x plus x. So equilibrium in terms of x is 0.0200 minus x. 0 plus x is x, and 0 plus x is x. But I know what x is. X is going to be equal to 29.2% of the SbCl5 that was decomposed. So this is where x equals 0.292. That's 29.2% written in decimal form of the original concentration. And that is 0.292 times 0.02, and that is 0.00584. All right, so that means that E, I'm going to change colors on you just so you can see this better. E now, not in terms of x, but for real, is 0.02 minus that value. And that is 0.01416. And this is 0.00584. And this is 0.00584. Now you want me to calculate Kc, no problem. Kc is equal to an expression. This is usually worth a point, and it's the easiest point on the page, where those square brackets mean concentration, where the C on my K means concentration. If you're doing Kp and you use the square brackets, you're going to screw this up. You're going to miss a point somewhere because we're picky about that. So my reactants are the same, so I can simply take their value, multiply it by itself, which is lovingly referred to as squaring it, and then I know this value of 0.01416, and I get, let the problem lead you, the values are sitting in your calculator. Take that and square it, and divide 0.01416, and I get, put that in scientific notation because it's small, 2.41. I have no reason to abandon my 3 sig figs at this point. 1, 2, 3 times 10 to the minus 3, and it's naked. All right. Now, if you had done Kp, I'm not going to work Kp out, but if you did, you should have gotten something in the range of 8.98 times 10 to the minus 2, and that's worth 3 points with all the work that you just saw me do to get this far. So how does the work break down? The work breaks down and you getting that subtraction done, and you getting that x equals this point and using it properly, and then 1 point for your final calculation. All right, in order to produce some of this antimony pentachloride, a 1 mole sample is first placed in an empty 2-liter container maintained at a temperature different from 182.C. At this temperature, Kc equals 0.117. How many moles of chlorine must be added to this container to reduce the moles of antimony trichloride to 0.700 moles at equilibrium? All right, new rice table. SbCl5 in equilibrium with SbCl3 plus Cl2. Okay, a 1 mole sample is first placed in a 2-liter container. Oh, but that's of the SbCl3. Okay, so this is 1 mole. Now, I don't know how much chlorine. That's what they're asking me. How many moles of chlorine must be added to the container to reduce the number of moles of SbCl3 down to 0.7. Alright, so I really kind of need to go back through molarity to do this properly. But what I also know is what let's see, what can I do with this? Start with the 1 mole. Oh well, let's just carry on. C, there was none of this to begin with. That I don't know. So at least I know which way this puppy's shifting. Well, the way it's got to shift is to make some of this. So I got to lose some of this, and I will lose an equal quantity here. So if I could figure out the equilibrium concentration of X, I may be in good shape. So what do you want me to make? You're telling me, oh, I'm going to reduce the number of moles of SbCl3 to 0.3. So this is going to go, X is going to equal 0.3. Now this is easier and I'm making it. Okay, that's going to be 0.3. Then, because that's what I lost, how do I know? Because at equilibrium, this is supposed to be 0.7. Let me double read this and make sure I've got this right. Okay, in order to produce some SbCl5, a 1 molar sample, got it, of SbCl3, got it in the right place, got it on the initial line, first placed in an empty 2-liter container, I'll worry about concentrations in a minute, at a temperature different from 182. At this temperature, Kc equals 0.117. I'm going to need that. How many moles of Cl2 must be added to this container to reduce the number of moles of SbCl3 to 0.7? So I lost 0.3, indeed. That's the hardest way to say you lost 0.3 I've ever seen. Okay, so that means that for whatever I had up here for the chlorine, I also lost 0.3, but it also means I lost 0.3, or I gained 0.3 over here. So therefore, plus 0.300 moles in the 2-liter container. So I'm going to work from that and say, well, isn't that 0.15? Yes, it is. 0. Therefore, 0.15 molar when it's all said and done here. So now let's figure out the molarity over here, and then I can use my K value, they gave me a 0.117, and find the molarity of chlorine and work backwards to moles. Whew, okay. So therefore, the concentration of the SbCl3 is equal to this many moles divided by the 2-liter container, which is equal to 0.35 molar. I can do that in my head. Okay, so now what does that mean? That means that I can solve for Cl2. Okay, so K in this case is Kc, and it's equal to this, which we know, times this, which we don't know, but we seek, times this, which we know. We know it's 0.15. We know the SbCl3 is 0.35. It can solve for Cl2. I know the whole shooting match is equal to 0.117. Sorry, that's a Texas expression. I slip every once in a while. So that's really equal to 0.35 times the Cl2 that I seek over 0.15 when I put all of this in molarity the way Kc is supposed to be done. So the trick on this one is they're annoying me by having to go back between moles and molarity. So therefore, the concentration of Cl2 is equal to 0.117 times 0.15 over 0.35. There's a couple algebra steps in there, but I did it in my head. I'm solving for this, so I'm going to cross multiply my 0.117 times 0.15 and then divide it by 0.35. So that's where I came out with all of that. I promise it works, but if you need to do the couple of steps of algebra, go for it. And so now that is simple enough to figure out in here, but I'm going to clear my screen because it's a mess. 0.117 times 0.15, get that numerator divided by 0.35, and I get 0.0501 molar for the chlorine. So the chlorine here in my E line is 0.50501 molar. So what does that mean? That means that I had twice that many moles because, see, remember that split over a 2-liter container? So therefore, if you need to see it worked out, therefore moles of Cl2 is equal to 0.501 0.0501. Moles per liter times 2 liters. See how that cancels? So I'm doubling this essentially to be 0.1 mole, just mole, at equilibrium. So here is 0.10 moles. That's a decimal. Therefore, this was 0.3 molar, because it's got to be the same as this. So this must be 0.300 moles. I left that naked and I shouldn't have. So therefore, wouldn't this have to be the sum of those two things? Therefore, started with 0.400 moles. Wow, that was painful for 2 points. At some point, you have to learn when to fish or cut bait. If you feel like you had just blazed your way through the first 3 parts of this problem, sometimes you got to look at the clock and go, hey, I've spent my 10 to 15 minutes on this problem. I got to cut bait. I got to just quit and move on because I've gained everything up to this point. I'm feeling confident about it. It's okay. This was a tremendous amount of work. This is what I call a time bandit. This took a lot of time. And so you only got 2 points for all of this work. 1 point for finally getting to here and 1 point for figuring out what X was back wherever we were, 0.3 molar. Getting that. That was it. Whew. That was ugly. All right, moving onward. 1992. Let's see what happens to us here. Solid. Ooh, trouble with equilibrium, huh? Solids. Solid. That means my K expression is really easy to write. K equals whether I want to do concentration or pressure. I haven't read yet, but K, before I put anything on it, is going to be H2O. If I do Kc, it's going to be this times this. And because it's going to be over 1, because this doesn't count and this doesn't count in terms of the equilibrium expression. So solid sodium hydrogen carbonate decomposes on heating, again with the heat business, according to the equation above. A sample of 100 grams of the solid was placed in a previously evacuated 5-liter container and heated to 160 degrees Celsius, but we won't fall for that. That's 433 Kelvin. Some of the original solid remained, and the total pressure in the container was 7.76. I'm feeling Kp coming on. So Kp is going to equal the pressure of water vapor times the pressure of CO2. Calculate the number of moles of water vapor present at equilibrium. I'm going to need some more room. All right, so let's rice this baby. 2 NaHCO3 in equilibrium with Na2CO3, which is also a solid, plus H2O, which is a vapor, and CO2, which is a gas. None and none. So what's going on? Calculate the number of moles present at equilibrium. 100 grams. That gave me everything I need. So at equilibrium, I get PV equals nRT. Therefore, N total equals P total V. Because it wasn't just the pressure of one of these components, it was the pressure of both. So the little word total could have messed you up on this one. Total pressure. But it's a one-to-one stoichiometry. So when I get the total number of moles, I just cut it in half. Over RT equals 7.76 atmospheres total over total volume R and 433 Kelvin. So kelvins cancel, atmospheres cancel, liters cancel, 1 over moles a mole, and I'm seeking moles, so that's a good thing. I'm going to get total moles. So 7.76 times 5, I'll get my numerator, divided by, open a paren, alpha R times 433. I missed a 4. Close the paren. 1.09 therefore the pressure of H2O equals 1/2 of 1.09 atmospheres at equilibrium equals, well, why did I do 0.2? That was dumb. I also could do it in my head, right? 0.545. How many sig figs do I need? 3. 3. 3. I'm going with 3. And this would also be 0.545 moles if I need it later. So, pressure of H2O, 0.545 moles. What you got so far? That's 3 points. Good grief, Gertrude. Okay, so that means a point for subbing the P, the V, the R, and the N. So a point for just using PivNert properly. A point for the 433, not being fooled by that. And a point for the final answer, realizing that you have to cut that in half. How many grams of the original solid remain in the container under conditions described in Part A? Well, if you produced 0.545, I really should have made it 546, huh? Oops, wrong color. Now that I'm looking back at my calculator, I misrounded because I want to use that number. I don't want to screw the rest of this up. You still get some forgiveness there, so if you do the same thing, it's not a big deal. You still got your points. All right, so back to the stoich. If I made, it's a 2 to 1 to 1 to 1 ratio. If I made 1 mole of carbon dioxide, and that's 0.546, and 1 mole of water, and that's 0.546, the amount of the NaHCO3 would be twice that, which was that 1.09 I had a minute ago. So, therefore, how many grams of the original solid remained in the container? 1.09 moles of NaHCO3 reacted. Looks like another decimal place. I don't want it to. Times the fact that there's 84.01 grams. Did they tell me that? I figured that out. I figured that out. You're going to have to get that molar mass. So get that molar mass. That would be 22.98 for the sodium, plus 1.01 for the hydrogen, plus 12.01 for the carbon, plus 3 times oxygen is 48, because there's 16 apiece. Oh, didn't need a paren, sorry. Delete the paren. Enter. 84. I got 84.01, but close enough. So, grams per mole. And that's going to come out to 91.6 grams reacted. Therefore, 100 grams that you started with minus 91.6 grams reacted is going to equal 8.44. Now, the first time I worked this with that different molar mass, so I may have made a calculation error somewhere. I'm looking back through my math. I got 84.01 times that. Okay, so I got 91.7. But then when I did this, that would have been 8.31. I got 8.44. So that's about close enough. So it's a matter of rounding. So somewhere in the range of 8.3 to 8.4, and you're good to go. That's how much remains. Okay, so write the equilibrium expression for the Kp constant and calculate its value for the reaction under the conditions in A. So they've given us all the pieces. We just need to plug and chug them. So they're finally getting around to the equilibrium piece of this. So Kp is equal to the pressure of the water vapor. I wrote it up at the top of the page, but I'll rewrite it here. Pressure of CO2. All right, which was equal to where'd it go? Oh, 3.88? What was my atmospheres? Oh, I don't have the atmospheres, but I do have pressure total. And pressure total is just the sum of the parts. So each one of them, pressure total was given as 7.76 atmospheres. Therefore, the pressure of the H2O is equal to the pressure of the CO2 is equal to 7.76 atmospheres divided by 2. Gives me 3.88. So that is 3.88 times 3.88, which equals that number squared. 15.05, 15.1 2 points for that. Knowing the expression, getting the expression on paper, this is why I make you do it. I know you don't want to, but you're just going to have to build a bridge and get over it. And a point there. So 2 points for that whole piece. And then if 110 grams of solid had been placed in the 5-liter container and heated to the same 160 degrees Celsius, what would the total pressure have been at equilibrium? And explain. I call this the easiest question on the page. You may call it a trick. If they increase the amount of solid up here, and they don't change the temperature, the value of K stays the same. Solids are not in the K expression. So the total pressure will remain the same. .76 atmospheres. Oh, that's not the total. No, that was the total, 7.76 atmospheres, since some solid remained unreacted when 100 grams was used. You're not going to shift this equilibrium unless you change temperature. So if you stayed at the same temperature, the equilibrium is the same, the pressure will be the same, the concentration or pressure of each of the components that participate in the equilibrium expression will be the same. Changing from 100 to 110, not going to make a difference. So when 100 grams was used, and you didn't change the temperature, you're not going to shift the equilibrium without changing the temperature. So you got a point for that explanation and a point. This was worth 2 points. Wow. Okay, so a point for saying it was the same, but also giving the actual value because they asked for it. Can you read the question? And then 1 point for talking about the temperature remained the same. That's part of your explanation. All right, we might be able to squeeze one more in. Let's try. Let's try to squeeze one more in this recording before I have to make another recording. All right, so we are at 1992. Yeah, if we can get through 1995, we'll finish off the 90s. So let's go to 1995. When hydrogen gas is mixed with carbon dioxide gas at 2000 K, equilibrium is achieved according to the equation above. In one experiment, the following equilibrium conditions. This is happy dance moment. They just told you the E line, no searching for X. So this is at equilibrium. I've got 2 moles of gas on the left, 2 moles of gas on the right. Therefore, in case they ask me, delta N is 0 and Kp equals Kc, and I can explain that nicely too. So let's go into the land of stoichiometry before we go to the land of equilibrium. What is the mole fraction of carbon monoxide in the equilibrium mixture? Now, I know you're used to doing mole fraction in, well, moles. But you know what? You can do it in molarity too, because all of these things occupy the same container. So the volume of that container will drop out. So let's just pick up the one in question, which is CO. So the mole fraction of CO, that's Greek letter chi. That's what I use for a symbol for mole fraction. Not everyone does. Some people use an X, but I think it's really supposed to be a chi. CO is 0.55. So you always want to have a habit of putting that right down here, because the most common mistake students make is they forget to put that part back in the hole. So part over whole is all I'm looking for here. So that's my part. And the whole was 0.55 and 0.55 again. Since both of these things were equal to 0.55, I have 4 parts here. See them? 1, 2, 3, and 4. Must count for all of them. And then 0.2 and 0.3. I'm apologizing now. I feel a sneeze coming on. I'm going to try to fight it off, and my sneezes are loud, so you may want to take cover. It's 0.55 divided by parentheses 0.55 plus 0.55 plus 0.2 plus 0.3 equals 0.3. How many sig figs? Well, they gave me 2 and everything, so I'll use 2. 0.3. Round that puppy to 4. That was a pity point. That was, I'm sorry, baby, you know no equilibrium whatsoever because your teacher never got there. Because a lot of people wait till the end of the year to do it, and they're racing to get through it all. We moved it to the first semester while seniors still care about their GPA. So, part B, using the equilibrium concentrations given above, calculate the value of Kc, the equilibrium constant for the reaction. Well, I should have figured that coming with those square brackets everywhere. So Kc equals, looking at the balanced equation, concentration products raised to the power of their coefficients over concentration of reactants raised to their power of their coefficients. I think I got it all written properly. So that is 0.55 quantity squared over, so I'm just looking right here, 0.2 times 0.3, which way do I want to plug it in? 0.3, 0.2 equals 0.55 quantity squared divided by, open a paren, 0.3 times 0.2, close the paren, got it, 5.04. 2 sig figs? Yeah, still 2 sig figs. 5.0. I know it freaks you out sometimes when the numbers come out that round, but don't let it. We've worked enough problems. If you're still listening, God love you. We've worked enough problems to know that that happens sometimes, especially in like kinetics and stuff. Oh, look, the politically correct equation. I kind of felt it coming because you started me off with gases, you gave me concentrations, then you asked me to calculate Kc, so it's logical for you to ask me to now calculate Kp. Politically correct because that much I could always remember, but my Steve Manikas taught me back in the Clinton era that this term was politically correct. And so I always had trouble remembering, does it Kp equals or is it Kc equals? I've never had a problem since Steve taught me that. So, God love you, Steve. I know you're somewhere in your 30s now and you have kids that are probably in high school. So, we also know that delta N is equal to 0. Therefore, the RT to the delta N is equal to 0. Oops, no, it's equal to 1. Sorry. Therefore, Kp equals Kc equals 5.0. This was the piece they were looking for. This was only worth 1 point. So you either got it or you didn't. And I don't think that you had to put the 5.0 because it says in terms of Kc, but they wanted to make sure that you understood. So if you stopped with what I wrote above, that delta N is 0, therefore Kp equals Kc, that would be all right. But I think it's better to just finish it off in case you didn't read the problem correctly and get in that habit, because it might have asked for the value, in which case you'd have had to put the 5. All right, now I'm changing temperature, aren't I? We were doing this at 2000 Now the system is cooled from 2000 to a lower temperature. 30% of the CO is converted back to CO2. Calculate the value of Kc at this lower temperature. All right, now you're going to make me do a rise table, aren't you? The only way to do this is to actually go through the whole rigmarole. So R is CO2 plus H2 in equilibrium with water vapor. Everybody's a gas. I'm being sloppy with my little g's. I is 0.30, 0.20, 0.55, 0.55. If I didn't have any other pieces of information, I would have to come along and do a Q and figure out which way to shift, but they gave me a hint. When the system is cooled to a lower temperature, 30% of the CO is converted back to CO2. So lose some, make some is my change. So E in terms of X is 0.30 minus X for that one. 0.20, that's not a minus, sorry, it's a plus. Plus X for this one. 0.55 minus X, 0.55 minus X. I know what X is. X is equal to 0.30 because that's 30% of CO's original value of 0.55. Well, that looks retarded now. 0.55. Therefore, X equals 0.3 times 0.55, and that's 0.165. I'm going to switch colors on you now because I think it helps your brain process this better. Therefore, the E line is 0.30 plus 0.165, which you can probably do in your head, is 0.465. And this E line is 0.2 plus 0.165, which is 0.365. 0.55 minus, I can't do that in my head. Not today. Not at this late hour of the day. All right, so 0.385 twice. So Kc is equal to all of that stuff put into the proper expression. Still looking at the balanced equation. Point 385 squared CO2 is 0.465. 0.365 for the H2. So what I got sitting in my calculator, squared divided by, open a paren, 0.465 times 0.365, close the paren, equals 0.87. Why am I going back to 2 sig figs? Because my first one was done in 2 sig figs. Oh, because the equilibrium concentrations they gave me are all in 2 sig figs, that's why. All right, that was worth 2 points. A point for solving for X. So, smiley face if you solved for X, because that was easy. Even if you didn't know how to do the rest of it, you should have at least gotten that, so you got a point for that. And then 0.87 for actually getting the answer. You had to work a lot harder for the second point. In a different experiment, 0.5 moles of hydrogen gas is mixed with 0.5 moles of CO2 in a 3-liter reaction vessel. So volume is 3 liters. 0.5 moles of CO2, 0.5 moles of H2. Still at 2,000ths, then my K still holds. I still can use that K value, which was 5, or whatever you calculated up there. So calculate the equilibrium concentration in moles per liter of CO at this temperature. R equals CO2 plus H2 in equilibrium with H2O and CO. It's not very pretty, CO. So they gave me the CO2 was a half mole over 3 liters. So that is 0.5 divided by 3. I'm going to call that 0.17. And that is molar. So that's my I. So what does that mean? they gave me the same amount of H2 and CO2, so I figured that out once, so that's still 0.17 molar. None and none. So what's going to happen now? I'm going to lose some, make some, all the same because it's 1 to 1 to 1 to 1 stoichiometry. E in terms of x is now 0.17 minus x, 0.17 minus x, x, and x. I'm adding these two lines together. 0.17 plus a minus x is 0.17 minus x. 0.17 plus a minus x is 0.17 minus x. 0 plus x is x, 0 plus x is x. So, k equals a number, and it equals an expression. I'm not going to rewrite the expression. I've already written it in this problem, so I've already gotten my point for that. They're not going to give it to me again, so I'm going to cut to the chase. It's going to equal x squared over 0.17 minus x, the term squared. And that's equal to a number that we've already figured out before because it didn't change the temperature. Happy face. K is still 5.0. So if I take the square root of both sides, square root of 5 is equal to x over 0.17 minus x. Cross multiply that square root of 5 across that parentheses term on the denominator, collect like terms, and solve for x. So, square root of 5. 2.27 times 0.17 minus x. I'm going to do that all in one step. I hope that didn't lose you. Just cross multiplying as well. So 2.27 times 0.17 is 0.380 minus 2.27x equals x. Add 2.27 to each side, and I get 0.380. That looks weird. Is equal to 3.27x. Therefore, x is equal to 0.380, still sitting in my calculator, divided by 3.27. And that's equal to 0.116, which I'm going to call 2 sig fig 0.12 molar. Isn't that what they wanted? Calculate the equilibrium concentration in moles per liter of CO2. Oh no, CO, thank God, CO. So that's what x equals. I'm going to put the CO just to make it clear. And that was worth a point. So you got a point if you got this far, and you got a point for all this work. But again, I say this is the second problem in a row where there was a whole lot of work to get 2 points at the end. So if you're rocking and rolling, you need to keep an eye on the time. When you do not want to spend all of your time for the whole free response section on just working a tedious equilibrium problem. So budget your time as well as your resources. You don't have to start with equilibrium either. If that's not your favorite thing after, I don't know, you've listened to hours and hours of me, it's okay. Don't start there. Go to number 2 or number 3. You got 3 problems to work with your calculator once you pop open that free response section. If equilibrium is your weakest, then for the love of God, save it for last. If it's your strongest, start with it. Have a little bit of test savvy going on. So once again, I thank you, loyal followers, for your kind attention. I hope this has been helpful. I hope you make good quiz and test grades as a result, especially on your AP exam. So join me next time. We'll carry on with this, move on into solubility equilibrium, work a whole bunch of solubility equilibrium problems, move on into acid-base, work a whole bunch of acid-base problems where I will rock your world with how I do buffers. Something to look forward to. All right, thank you so much, and I hope you have a great rest of your day. Clearly, it's time for me to quit talking.